All right, welcome everybody. This is Jonah Hobson, a marketing manager at ITI, and this is the Showcase webinar series. Today's presentation is titled Safe Lifting and Handling of Rebar Cages, Deep Foundations. Very good topic for a lot of our construction clients, and but really the principles that Vince and Benjamin are going to talk about really apply to any kind of rigging and lifting. So for new folks that are joining us, I'm just going to touch on a very quick intro for ITI, who we are and what we do, and then I'll hand it over to Vince and Ben. So at ITI, we strive to be the world's foremost provider of educational and technical services for those who use cranes, rigging, and load handling equipment. So what does that really mean? In the simplest terms, from the owners and founders of our company all the way on down to every employee, everybody at ITI has a strong desire to help people, and in this case, obviously, with cranes, rigging, and load handling being the focus. You can see on the screen there, we've been very fortunate to work with global leaders from all industries, and I can touch on that a little bit more on this next slide. To bucket everything we do, we kind of do it into four separate groups: so cranes, rigging, lift planning, and engineering. And as you can see on the slide here, this isn't limited to 1, 2, or 3 industries. We work across all industries: chemicals, oil and gas, DoD, hydro, nuclear, railroad construction, everything. Anything where we're moving large or significant items, and most of the time lifting them as well. So this is just a different grouping of our courses, kind of broad categories of what ITI offers. You can see it goes all the way from rigging engineering training to lift planning, all the way down to heavy equipment training. Just so it's everyone's aware, this applies to all skill levels, from the most advanced folks who might take our Master Rigger course or the rigging engineering program, all the way down to basic rigging and inspection. If you want more information on any of the courses, visit iti.com/training, and then you can dial it down from there. So training is the core of what we do at ITI, definitely, but we have some other divisions that either supplements or can be in place of that training. So first is e-learning, and again, this is the best one that can be a supplement to instructor-led training, or they can stand alone if you're trying to train a lot of people at a time. We have a bookstore. It's probably it is the largest bookstore that has to do with crane, rigging, load handling products. Lots of great resources there. If you guys have some time, definitely check that out. We have a consulting or field services branch where our technical experts head out and they provide different services such as crane and rigging audits, accident investigation, things like that. A workshops division, which is a regional kind of conference setting where cranes and rigging and load handling are the focus. We have a couple of those scheduled for 2016. Houston and Edmonton are confirmed, and stay tuned for that. We can see where else we'll be headed in 2016. And finally, webinars, which everybody's familiar with because we're on one right now. So normally, Mike Parnell is the host of these webinars. He's unable to join us today. He's actually attending the ASME B30 meetings in New Orleans. As you can see, he volunteers his time quite often with ASME, helps to set the standards when it comes to lift planning, the crane and rigging main committee, and along with his wife, Darlene Parnell, they were the founders of ITI in 1986, so we're celebrating our 30th anniversary this year. We have Vince Siefert. He's going to be our leader on the presentation today. This is actually the second time that Vince has joined us, so just a ton of experience as a construction engineer. You can see some of the projects he's worked on there: the Brooklyn Bridge, Manhattan Bridge, most recently the Tappan Zee Bridge in New York. He founded Siefert & Associates in 2000, and we're very, very grateful to have Vince on the line. And then helping him out today is going to be Benjamin Harmon. Ben is engineer in training with Siefert & Associates, and he's a civil engineer graduating from Northeastern University in 2015. So this is a pretty nice bonus. We didn't promote this too much, but this presentation today is actually eligible for professional development hours, or PDHs. So pay attention to the presentation today, and then at the conclusion, visit iti.com/pdh. You'll just take a short quiz following the webinar. Be sure to enter the correct email address in there so we can email you the certificate of completion. I know. Oh, we're going to leave the quiz open for the rest of January. So on February 1st, the quiz will not be available. So even if you're watching the recording of this webinar, as long as you complete the quiz before February 1st, you're still eligible for those PDHs. And with that, I think I've talked enough. I am going to turn things over to Vince and let him take it away. And we're just switching the screen here. All righty, Vince, we can see your screen. I think you're ready to go.
Excellent. Well, thanks a lot, Jonah, for the intro and the kind words. This is Vince Siefert speaking. Ben Harmon will be next. Preparing you to speak about somewhat obscure topic, rebar cages, with the emphasis on deep foundations, as they're the longest and heaviest usually on the site, notoriously difficult to not only engineer, but to lift and handle. And we've got to admit, we're not experts in this field, although we have experience on a dozen or more projects. I would say, in fact, this is probably the only field I know of in a heavy construction environment without a recognized expert. The closest guy we could probably say is that man is Dr. Ahmed Attani at the University of Nevada, Reno. And the last time we met with him, we agreed this topic has been flying under the radar for too long, and perhaps its time has come. Because we know it's a notoriously dangerous operation. It's really the most critical lift often on any job without any governing code or standard. So speaking of other notorious situations, what comes to mind when I was putting this presentation together of what it would feel like to be underneath a mess of flying arrows, which would be similar to having a number 11 bar with your name on it under a disintegrating rebar cage. And just like jarts, it was intended to be a harmless family game. In fact, they're truly steel projectiles. They're very dangerous, notoriously so. So now that they're not around anymore, we could talk about serious challenges we see and the danger on our job sites for a collapse of a rebar cage. And it could be on land or water, but either way, these collapses usually occur without much warning. And it's no surprise, because in reality, most of the erection and engineering is being done based on experience and rule of thumb only, trial and error. And unfortunately, errors are painful. And just to make it clear, we don't have too many pictures of foundation element failures because they're pretty much cleaned up quicker than a column collapse like these. Either way, it's a big problem. And besides the obvious material damage, equipment, probably especially considering the time lost to the cleanup and refab, and the unlikely, or rather the likely investigation that's going to pursue, this is the big problem. And possibly consider this as a bigger problem, huh? Damage, death and injury. Certainly was a big problem for Eduardo here in Brazil. Thank God he survived. Rebar projectile going right through his skull, missing his brain. So clearly action is needed. And there's no simple solution. Well, the rebar caps certainly address the #1 cause of death on construction sites. Hard hats alone are not sufficient to protect the workers from falling rebar. And unfortunately for Dr. Attani, the funding has been very difficult to secure for additional research. And this is because he's been told, because it doesn't affect the traveling public, and just contractor's employee, that funding is not warranted. So this is what we're going to be talking about today and try to promote the cause a little bit. We've already gone through the preface. First up will be anatomy of a rebar cage and some general crane and rigging practices, as well as the construction engineering challenges associated with them. There will be a brief intermission, and Ben's going to take over with the research findings from Dr. Atani. I'll speak about the current trends, and we're going to conclude with the best practices for the four main players, which I'm sure everybody in the audience is most likely one of the four, whether you're a permanent design engineer, contractor, construction engineer like ourselves, or a fabricator, erector. We'll give you some take-home, some take-back, and recommendations for future. So let's get started with the anatomy lesson. So shown here on a picturesque site in Manhattan is a deep foundation element drilled shaft in the foreground, approximately 6 foot diameter, prefabricated, ready to be erected, and in the center of the slide, a rectangular slurry wall rebar cage being fabricated by the men in the field. And typically in the city environment and the East Coast, these are field fabricated with our lathers or ironworkers, as you know, doing their best day in and day out, and we appreciate the quality of their work and efforts and all, and certainly don't feel it's fair for them to take full responsibility for the safe lifting and handling, as they often do. Becoming more and more commonplace is off-site fabrication, which obviously has the advantage of a controlled environment. And we know this is not always practical. And whenever possible, of course, I'm sure most contractors would take advantage of this option. Either case, tons and tons of steel are going to be held together with just some simple tie wire connections, whether it's done in the shop or the field. These are the 6 recognized types by Concrete Reinforcing Steel Institute. Upper left being the weakest, the single snap, and a double wrap and saddle on the lower right-hand corner shown as the strongest tie, and a little bit more on that when Ben speaks. Let's continue our anatomy lesson 101. For a circular drilled shaft, as our representative graphic here, besides the permanent steel, what we show here is the template bars, the template hoops, and the pickup bars. And by the way, this is from Dr. Atani's research publication, which primarily focuses on West Coast rules and practices. And we're going to also comment on some of our East Coast techniques. So let's first talk about the pickup bars. They're the 4 longitudinal bars that form a square, as the name implies. They're going to be used to pick up the cage and take it from horizontal through 45 degrees to vertical. These should be tied at every intersection with one of the stronger type ties. And as an alternative, sometimes we are using Crosby Clips or similar U-bolts to splice onto the pickup bars. More on that later. We talk about the template hoops or crush rings. Are spaced around 8 or 10 foot on center, ideally, tied 100% with a double U-tie or wrap and saddle. And again, there's alternatives that are starting to become more and more common, such as fabricated steel rings, which would function in a similar manner to these bars, which are number 8 or better. And then there's the all-important internal bracing, which every major element greater than 20 feet and 4 foot diameter should have internal bracing. Minimum 4 number 8 rebars, preferably 8 number 8s, spaced again around 10 foot on center, which are connected to the hoops at 100% tying, and also tied to the pickup bars. And once again, some of the practices we see more and more being used is structural steel or prefabricated internal bracing. So now that we've had our anatomy lesson, refresher course, because I'm sure you're all familiar with rebar cages in the audience, let's talk about the most critical operation, the upending process, and how the cranes and rigging are best solved, the challenges that we have. So of course, the contractor would always like to use one crane whenever possible, and certainly we concur, less equipment is better. And in this case, we show delivery, upending, and raising to vertical. For a cage, I think it's about 60 feet long. The advantage of the single crane is obviously lower equipment cost. Some of the disadvantages are that you have to drag it on the ground, typically, especially with one block. With 2-point and 2 blocks, it can be rotated in the air, as we're going to speak about in a little bit. So just to summarize, the single crane is preferred up to, and practical, up to about 60 foot in length for a rebar cage. Single rigging point for something 20 foot or less is easy. In a 40 to 60 foot range, typically you need 2 points of rigging. And then the 2 crane lift, often employed. The advantage of being able to suspend the load without dragging on the ground is going to preserve the integrity of the cage. Sometimes it's required due to site constraints, such as this particular photo where you have overhead lines. So we're talking about a 50-foot cage, which could have been upended with a single crane. There's definitely advantages of 2. And in this case, we're showing 2 particular cranes. One crane with 2 hooks could also accomplish a similar upending process. Up to 130 foot length is what we've seen being done successfully around here. And for the longer cages, or cages that are somewhat unstable, a tilt table is a really good option to consider. Here's a Cadillac version shown that was manufactured by Birminghamer for a project in Manhattan. It worked real well. And the way this works is it still requires 2 cranes. The one crane on the left shown is just raising the lift table, tilt table rather, from horizontal to near vertical at around 80 or 90 degrees. The second crane is going to lift the cage off of the tilt table without any rigging other than at the very top, and take, in this case, a slurry wall panel and set it safely in the hole. So speaking of rigging, there is certainly cause to speak about just the rigging for delivery, handling, and staging, because that's going to differ than the rigging for the upending process. Shown here is a nice situation with 8 rolling blocks and a spreader beam for approximately 80-foot unit, well braced, not much deflection, and just something to keep in mind that the rigging used for the initial handling is going to differ than the rigging for the upending. So let's look at some of these upending rigging drawings that we've compiled recently. And we're going to show you here a single crane with 2 hooks, and in the way in which it would upend a medium-sized rebar cage. So it's really important that both hooks, the main load line as well as the auxiliary load line, each of them have sufficient capacity to pick the cage on its own. Reason being is in the initial configuration, when it's laid flat, the auxiliary line is going to be capable of taking up the entire load. The mainline load would be slacked. And then what's going to happen is, through a series of rolling blocks, properly placed rigging and all along the mid-section of the shaft, on the right-hand side you'll see the beginning of the upending process where load is going to be transitioned from the auxiliary line to the main line. And eventually, as you can imagine, once it's vertical, the main line will have the entire load. Also worthy of note here is the rotation can be either in a clockwise fashion or counterclockwise fashion. And in this case, as in most, it's preferred to rotate it away from the crane. So whenever possible, I'm sure the operator would agree, he would rather not have the piece rolling in on him versus rolling away from him. So whenever possible, when the site allows it, this is the preferred orientation of the crane. Moving on to a upending process with two cranes. Crane 1 being shown on the left and the smaller crane 2 being shown on the right. We see a longer rebar cage with, again, multiple parts of rigging spaced appropriately for the stiffness of this particular cage. And again, the main load line is at the top of the cage, auxiliary line of crane 1. In the midsection in crane 2 is got two-part rigging to both keep the cage intact and also to keep it suspended while the tailing operation takes place. And ultimately, the main crane, crane 1, is going to take the entire load on its load line. So let's look at a picture of this exact operation in the field. Certainly, crane 2 looks a little bigger here in real life, shown to the left. And crane 1 can't be seen due to the length of its boom. You can see a little part of the crawler there on the photograph, and you can see the 8 parts, I believe, of sling spread along the body of this T-shaped slurry wall panel, which is starting to be upended with crane 1 and crane 2 in tandem. Of note, you'll see the main load line of crane 1 in the upper right-hand corner of the photo is actually slack, and it's connected to a custom fabricated lift frame, which again we'll talk about a little bit later. All part of the difficulties and challenges that we face upending these things safely, which this one definitely did. And a more recent photo, probably our most recent upending procedure shown here of a shorter cage, a single crane with 2 blocks, again taking this 40-footer, 50-footer, I think, the main load line attached to the top, whip line along the body of the unit with a rolling block. You see the horizontal configuration on a cloudy day on the left, and then miraculously the sun starts shining as we're upending this baby in beautiful Jersey City, New Jersey. Picture perfect. So let's talk about some of the construction engineering challenges we face in doing our work as a construction engineer. Number one difficulty, determining the structural properties of our wet noodle. A couple other noodles shown here. And basically, what we got to say, honestly, it's impossible to accurately define the rebar section properties, and we know general practice is to use trial and error methods. And that's fine when you're doing a trial, but not too good when you get the error, right? So there's got to be a more scientific way of accomplishing this, and ourselves and Atani have worked and talked about the moment of inertia calculation for a rebar cage, which is really the end game here. And we know we can't treat it like a pure beam. We typically would use the moment, parallel axis theory formula to calculate the stiffness property of a structural element. And as you probably recall, if you had this in statics back in engineering school, is that the moment of inertia is going to be the sum of the individual bar moment of inertia plus the product of the bar area times square of the distance. And however, you'll notice that a beta reduction factor has been introduced in the second part of the equation. And this beta factor is necessary because the connection strength, which we know is usually just tie wire joints that we spoke about a little bit earlier, they're not rigid. They're going to flex a little bit. There's going to be movement. How much? Well, that depends on a number of things that Ben's going to be speaking about in a little bit. It could range, anywhere from a 20% to 80%. There's no way it's going to be 100. Let's just say that's for sure. Since there's so many variables associated with this beta factor, what we really recommend is, after calculation has been done, a full-scale test be done in the field, a simple lift test, 2 points, a simple span where a deflection can be easily measured as a separate operation. And we know that's directly related to the stress and the deflection. So with that one test, the construction engineer can verify his calcs and possibly make modifications given the time. So we'd love to see that happen more and more. Again, we're counting on just plain old tie wire to give us the stiffness that we all need to get that cage safely lifted and handled. And unfortunately, there's often little or no oversight or specification requirements for what the tie wire even is, as far as gauge size, strength, or country of origin. And we've seen all sorts of things out there, from 16 wire to wire we don't even know what it is, white wire. The right wire that should be used, let's say, should be 15 wire minimum. 14 is even better. And the types of ties are very important too. There's a large range that has been quantified of the strength of those ties. Again, we'll speak about that in a little bit. And we want to get a F sub U, the ultimate strength of 40 KSI. Or better yet, use weldable steel. Welding obviously would give us much better, much stronger joints. Substituting grade A706 rebar for 615 is really not that much more expensive. I think around 5%. It does appear, though, that most states don't allow weldable rebar, and there's really no good reason. So something to be looking for as a future alternative. So finally, for anybody who was recently attending a webinar we did back in July, one of the 6 most important issues we spoke about during crane lifts was, number 5, the stability of the lifted load. Here showing a pair of plate girders for a pretty long bridge span. Obviously, there was a lot of oversight, a lot of engineering went into the safe lifting and handling plan for these girders. So the question I have is, what other critical lift is routinely performed on a job site without the requirement for a stability check? Well, the answer to that is that red-headed, freckle-faced stepchild, rebar cages. I'd like to say that there's, unfortunately, very limited available documents out there to guide all of the important parties as to how to successfully lift and handle rebar. First one to mention is Concrete Reinforcing Steel Institute Placing Reinforcing Bars Manual, but that only has a couple pages on prefabricated rebar cages, and it's really more geared towards a foreman, journeyman level. Not a bad document. It doesn't provide much engineering, though. The manual here, this research project done by Dr. Atiani, as far as we know, is the only research done in the United States regarding the stability of bridge column rebar during construction, and the focus is generally above grade columns, which are similar to deep foundations. And his research spawned this pamphlet put out by ASCE back in 2013, which is really short and sweet. It's about 35 pages and coincidentally costs about $35. So it does have the best practices. It's a start. It deals, again, mostly with above grade rebar cages, which of course are similar, and this is what we got. So this is what we use. However, we know that there's been hundreds, if not thousands, of successful lifts done every day, every week in the country. Unfortunately, there's been a few failures too. So all these, contractors, fabricators, engineers that are involved typically have all, lots of internal documents on their lessons learned, but they're not being shared. So this knowledge is not going anywhere as we wish it would. So at this point, we're at our intermission slide that I promised you. I just wanted to ask again a question. Do you ever feel like this? Hopefully not, because you want to be this guy. And part 2 is coming up in just a moment. This is a chance for everybody, if you want to get a coffee on the West Coast or a water if you're on the East Coast. If you happen to be in Europe, maybe it's time for a beer. And if there was any questions or anything that might need to be asked right at this moment, feel free to raise them.
Thanks, Vince. That's perfect. We don't have any questions at this time that came through. A couple comments, which are, thank you for those. I just want to remind people that you can ask questions. There's a question pane on your GoToWebinar dashboard there. So if something comes up, it looks like we'll have a little bit of time at the end. So please submit your questions to me, and I can give them to Vince over the air at the end. But yeah, do so in the question pane there. As Vince said, we're going to have Ben coming back on the other side with the second half of the presentation. And just another reminder too, if you do want those professional development hours, the website to take the quiz on is iti.com/pdh. So that's all from me. I had one question come in just now. I might as well answer it since I'm on the air. But we had a question about getting a recording of this presentation. So yes is the answer to that. We record all the showcase webinars. We'll post them on our website within 24 hours, probably sooner than that. But since you're registered for the webinar, you'll automatically get a link, an email with a link in it, taking you to the presentation recording. So that's all from me right now, and I'll turn it back over to Vince and Ben.
Okay, thank you. My name is Ben Harmon. I'll be starting the second half of this presentation for you guys. So, as Vince mentioned, I'm going to talk about the most recent research that has been done on the topic of stability of rebar cages. And as far as we know, this is the only major research that has been done in the U.S. and it was done 5 years ago, or approximately 5 years ago. So this is all we have, really, as far as scientific evidence and data goes. So the strength of the tie wire connections, as Vince talked about, is critical to developing enough bar area to have enough stiffness in your cage to get your high moment of inertia, high section modulus. And you can see here the varied amount of strength that you can get out of a connection based on the type of connection. And if you go from the weakest connection, which is the single snap, to the strongest, which is the wrap and saddle, you get a massive difference in in strength. And these three columns here basically correspond to forces in different directions or rotation. And you can see for every case, increasing the strength of the connection can be significant. And something we hadn't considered was that the experience of the iron worker making these connections is also a factor. In some cases, it can, having an experienced iron worker can increase the strength by 10 or 15%, which, when you're calculating the section modulus or the stiffness of the cage, that 15% can be critical. So Atani ran a nonlinear finite element analysis on a full-size rebar cage, 34-foot long by 3'8" in diameter, and he analyzed 4 load cases to see what the difference in stiffness is under different circumstances. The first case is that he just had the minimum number of ties, meaning that about 20 or 25% of the rebar intersections were tied. And then in the second case, he tied all the intersections, so 100% tied, and to see what the difference in stiffness is there. And then cases 3 and 4 just have a minimum number of ties, but they also implement internal braces. The difference between 3 and 4 being the type of internal brace, which I'll talk about a little bit later. But you can see the results that he got from that analysis, and he found that yes, tying every rebar intersection does improve the stiffness. It improves it by about 3 times, which sounds pretty good. But when you look at the increase in stiffness you get from adding internal braces, which can be up to 10 times, you can see what is a more efficient, action to take. Adding the internal braces is, a much better option. And if you do that, you don't have to tie every rebar intersection, which is a laborious task. And it's not necessary. because for every rebar that you tie, you don't get that much additional stiffness for it. So then Itani wanted to see if his analysis corresponded to a real-life experiment, if you could get the same results. So he built 2 full-scale specimens, same overall geometry. The difference in the specimens being the amount of rebar in the cage and the type of internal brace that was used. These are pictures of him loading the rebar cages to failure at his lab, and you can see how much deflection you get before this cage fails. You might not be able to tell from the pictures, but this is a relatively slow progressive collapse where you see the massive deformation before the cage finally fails, which is important because the sudden failures can be the most damaging failures. So adding internal braces does have that effect as well. So this data here shows the effect of having more reinforcement in your cage and what that does to the stiffness. So as construction engineers, we're not proposing that you add more rebars to a cage before you lift it. We're not adding rebar to the final design, but it is a consideration for the permanent designer. Maybe they can add more rebars to make the cage a little stiffer. Because there is some improvement, but as you'll see, it's not as significant as adding internal braces. Similar story with the type of tie wire connection used. You can get some improvements in the stiffness, by using the stronger connections, but at the end of the day, it's not enough to ensure the stability of the cage alone. This data is where you see the largest effect. You get a massive increase in stiffness when you introduce internal braces to your cage. X braces and square type braces are similar. Square type braces are a little bit stronger, as you can see from this data. And in both cases, you can improve the stiffness, like I said, by up to 10 times, which that's what you need to ensure the stability of the cage. That increase in stiffness. So I think you're starting to understand my point here is, the #1 best practice for a rebar cage lifting and handling is to add internal bracing. And this is the main point of our presentation here, is that when you have a rebar cage with a height to diameter ratio of 8 or more, bracing should be required. You can't ensure the stability of the cage without that, in those cases. As I mentioned, there's 2 types, which I'll show you pictures of in a moment. There's the X-type and square type braces. They both consist of #8 rebars bent into a Z shape, and they intersect and cross over the cage and to provide that rigidity. And they are tied to the longitudinal bars and to the end rings at every intersection. That's the one location where you need to make every intersection tied. So here's some real examples of what those braces look like. On the top left there is the X-type bracing. So it's 4 of those Z-shaped bars, and they cross over the center of the cage and intersect with the middle. And that intersection is either welded or tied together. The top right photo is the box-type bracing, which is similar. It still has the Z-shaped bars, forming X's, but they're on the sides of the cage. You can see here from this box we have drawn, the top and the bottom sides represent a pair of X braces crossing over. Similarly, 90 degrees to that, we have 2 pairs of those bars as well. Those green lines represent those bars crossing over. So the reason why the box-type bracing is stronger is you might be able to get a feel for it. There's twice as many bracing bars, with more intersections. Those intersections are also tied or welded together, so you get a little bit more rigidity with that. The box-type bracing has the additional benefit of leaving the center of the cage open for the tremie hose to make the pouring of the concrete easier. So it's a stronger design, and it's a more practical design as well. As I mentioned, the Z-bars should be tied to the pickup bars at every location so that they are properly engaged when lifting the cage. So this is a picture of a system that was developed by Dimension Fabricators called Cage-Right System. They designed and patented this system. It's similar to the bracing photos I just showed you, but instead of using template hoops, they use circular steel plates with notches around the perimeter for the longitudinal bars. So they're good as templates when fabricating the cage. And the brace and bars can connect directly to the steel plates. So they're welded to those steel plates in the shop. And then, so you can see, from this photo, you can see what it looks like, and you get a feel for the fact that it's very similar to the box type bracing that I just showed you. The benefit to this system being that it's all integrated into one system. They often fabricate these in their shop, and it can be a much stronger system because of it. Here are some photos of those cage right systems in the field with the cages being fabricated on site as well. Here's a design done by Skanska Koch for one of their projects. Very similar to the cage right system in the sense that it's a circular steel plate used as the template hoops. But instead of using rebar braces, they have rolled steel angle shapes that are connected to the circular steel plate to get you that brace in action. Here's a picture of what that looks like in the shop. You can see that the whole system is pretty similar. This is a system that is used in England. That it's similar, similar to what I've been showing you, but the system's slightly different in the sense that they have these ladder spacers that replace the X braces, and these clamped cage formers that take the place of the hoop or crush rings, so that the cage can be lifted and upended. This system is not found in the U.S. Currently, but we are researching how exactly it works and what applications it could have for our cages over here stateside. So I've just showed you a bunch of different good options for internal bracing. Here's a picture of not so good option, something that didn't work out too good. You can see with this cage there is internal bracing with the rebars crossing over the center of the cage, and then the supplemental timber bracing, but obviously it wasn't enough to ensure the stability of the cage. The cage still failed when it was lifted. So the moral of the story with this slide is that it's not enough just to have the braces. They have to be designed by a qualified engineer and erected by a competent contractor who has experience with these types of cages. So here's some photos of a shaft properly being upended. You can't really see the braces in these photos, but they're there, and you can see how low the deflection is. You're not really getting a wet noodle effect from this cage here. Similarly, this is a slurry wall cage in New York City that's being lifted with 2 cranes. The big crane on the left there has 2 hooks. It's eventually going to place the cage in the hole, but there's a smaller crane there. You can see it behind the bottom of the cage. It's just holding the bottom of the cage so that it can be rotated in air and not dragged on the ground. Once the cage gets to vertical, the smaller crane is disconnected, the big crane is taking the full load, and then it can be swung into position to be placed in the T-shaped hole made right for it. So that's a good example of a successful lifting operation. I have a short video clip to show you a circular steel cage being upended. See if I can play this here. Okay, here we go. So you can see the internal braces on this one, spaced at 10 foot on center maximum. You can see the low deflection on the cage because of those braces, and it looks pretty easy because when you do it right, you get a pretty easy operation. I'll play that video again for you guys. It's pretty quick. Pardon my thumb in the bottom corner there. You only get the video once, But it's a video perfect operation done there. So now my part is over. I'm going to pass it back to Vince, who's going to talk about some of the current trends in the field and go into some of the finer details of the lifting and handling of rebar cages.
All right, Ben, thanks for that. And we're on the final stretch here. where we're going to talk about the current trends we're seeing in the field, mostly on the East Coast. And not sure what's going on in the middle coast. We know what's going on the West Coast, probably a little bit of both in between. So basically, though, we know that people are looking to erect longer and longer cages, and why not? Associated with that is going to be how to lift them, and lifting rings are becoming very popular in lieu of pickup bars. Connections as an alternative to tie wire would be U-bolts, and then there's related temporary supports necessary, and dealing with those embeds and instrumentation we've all come to love. So let's first talk about a project that consists of 180-foot final condition shafts, which is exactly that project Ben just showed the video on. Koch's job we worked on with them at the Kosciuszko Bridge in New York City. So first choice would be to pick it at 180 feet. That would be difficult without a tilt table. That option was ruled out. So the next option would be to take it into two 90-foot sections with one splice, or 360s with two splice. So, you know, this decision is important right here because this dictates everything: the crane choice, the rigging, the lift methods, and all the hardware that's associated with it. So it was ultimately decided, right or wrong, to use 360s in this case. You know, just a quick note too, typically we find that, you know, the weight is not evenly distributed in a rebar cage, typically heavy at the top. And that makes sense, right, because you have the higher shear in the final product. It just makes it difficult, though, to erect pieces when you have erratically spaced bars. I think, you know, permanent designers in the audience could learn from this that a few extra bars sometimes is going to make life a lot easier for the erector at a minimal cost. A little bit more on that later. So the lifting ring, as I was mentioning, as an alternative to hoops and crush rings at the top, the picture shown here of an example, again at the K Bridge, as we call it, a stress contour, three-dimensional finite element analysis output is shown here, showing the calculated stresses. And because they're such a good contractor, I wanted to show their detailed shop drawings too. First showing a plan view at the top, showing a bundle number 18. So they have two number 18s that had to be swallowed by a specially designed U-bolt, which is connected to the lift collar to secure everything properly. So despite all their calculations and thoughtful drawings, they did the right thing also by performing a full-scale load test. And shown here is that lift collar being attached to a nearby dock they have. And all that sound engineering resulted in a great successful operation as shown here, 60-foot shaft being ready to be lowered into the ground. And also wanted to further demonstrate this cap. I'm trying to find my cursor. Here we go. So the lift frame, I have a little animation here to just really drive home the point of how they constructed this and fabricated it. So you start with two halves of a structural steel collar, spliced at the joints with conventional bolts and splice plates on the top and bottom flanges. Bolted up nice. Next, you have the custom U-bolts, which were also tested in their shop, bolted to the lift collar with the rigging plates and shackles ready to go. So speaking of connections, what's really common is to use Crosby clips, or technically wire rope clips, to connect rebar. Many ways. One is, you know, the longitudinal bars to the pickup bars. Other times you'd be using Crosby clips or similar to connect to support frames, lifting collars, etc. The bottom line is, while these are a great mechanism to use and we highly recommend them, they must also be tested. And the reason being is the catalog is talking about wire rope to wire rope connections of equal diameter. And what we know is that people are going to want to use different size bars. They're going to need to connect different size bars together, or a bar to a plate, or a bar to a channel. All these different combinations Doesn't cost that much. Need to be tested in the presence of an engineer or out in an independent lab. And once those results are obtained, we recommend using a factor of safety of 2. So here's an example of a lift frame plus a temporary support plus some of these U-bolts that was performed on a project in Manhattan. Here showing a simple lifting channel, right? Some of the best details are the simplest. It's channel connected to the bars with the Crosby Clips, and here's a temporary support, similar type construction. The rebar cage being suspended on the guide walls for a slurry wall with the channels and the Crosby Clips. And here's a photo of that exact operation in progress. Again, a lot going on here. What I just wanted to point out is on top is some lifting frames that are connected to pickup bars, which are actually extended above the hole because this is a top-down construction job like most slurry wall jobs. And this cage had to be lowered about another 10 feet. Temporarily, though, it's supported on these supports on the guide wall, which again are just simple channels with the Crosby Clips holding it in place, getting ready to be concreted. Quick word on embeds and instrumentation. We know they're necessary. You know, we know that also it seems to get fairly congested with a lot of unique shapes required, and in particular, you know, we get a lot of O-cell needed, Osterberg load cells, that is, at the bottom of drilled shafts. We know they're important. We know they need to verify the design capacity of the drilled shaft. Also, we know that it's difficult to get concrete around them, just like any embed or block out. So, you know, the O-cell shown there on the bottom. A little detail we found that works well is to create a funnel shape with the rebar to more or less force that tremie hose to be centered right over the hole in the O-cell to assure that the concrete gets underneath and all around and above that O-cell, completely encapsulating it. So this is one trick we'd like to see used more often. And finally, speaking about embeds, here's probably the largest embed we ever dealt with. It was so big, in fact, that eliminated the need for the pickup bars, and the bars were actually connected to the embed. Might be a nice picture. It was certainly not an easy job, but it is done at this point. So let's move on then to the summary of everything we've learned today. For the best practices, starting for the #1 person, the permanent design engineer. So what we'd like to say is that whenever possible, you should consider increasing the stiffness of the rebar cage. How do you do that? Increasing the quantity and size of longitudinal bars. As Ben mentioned in his graphs, they provide additional strength. Of course, specifying internal bracing, it should be a must. Minimum 4 #8s, 10 foot on center is a good start. We know that 8 in the square configuration is even better, or structural steel even better. Allow the bracing to remain in place, and if you're concerned about seismic design, keeping the flexibility in the system, well, try to account for it. There's ways to do so. Batani's document is available. Allowing use of weldable rebar would be great, and we know that many states and authorities don't allow it. It's starting to become more and more common. It's not a big cost impact. It would really, really stiffen up that cage nice. So designing with constructability in mind, of course, is always a goal. Should anticipate that splicing will be required. Try to avoid irregular rebar density, like I said, like it's typically heavy at the top. If we ran some of the bars a little bit longer, just not go from ridiculously heavy to ridiculously light cages. A few extra bars is going to aid in the lifting and handling. On the same project, there's no reason to have 6 different or 8 different size shafts. Each one of them requires special tooling and equipment, as well as rigging, crane, lifting and handling practices. And I don't know if you hear my radiator there in the background, hopefully I'll talk over that. So we want to avoid multiple diameters. You might think you're saving money, and in reality, it's probably a wash if you just have a couple sizes. And consider the difficulty associated with your embeds, blockouts, and instrumentation, especially if they're in the same element. If we could spread them out over a couple elements, it'd be much preferred. So now let's talk about number 2 guy, the contractor. You need to have a proper and safe lift plan and cost-effective execution with the emphasis on cost and safety. So be prepared to utilize, cranes with 2 blocks at a minimum and 2 cranes whenever possible. Consider all your ramifications when you make that decision on when and where to splice. The tilt table is a nice option to have in your back pocket for very long cages or unstable cages. Look into offsite fabrication whenever possible. And take some of the responsibility, share some of that responsibility, I guess you'd say better, with the fabricator or erector. It's not fair, as earlier stated, to put it all on the foreman and journeyman out there. And include your construction engineer on all your aspects, whether it's in-house or an independent consultant like ourselves. Really every step of the way, there's some valuable time that can be spent, learning from each other. And when you get to the end game, the concrete placement, each job you might say is unique with the embeds and blockouts and instrumentation. Got to get clever on how to make sure that it's fully encased. Using bracing in a square pattern is best, as Ben was saying, puts that trimming hose right down the bottom, and of course pour it as quickly as possible, which I know you want to do anyway. Even if it requires a couple hours of overtime, nobody likes to leave that hole open for long for a number of reasons. So we come to the number 3 guy, the construction engineer, like ourselves. Our number 1 difficulty, getting that structural integrity. Whenever H/D is greater than 8. So you must design internal bracing, again, with the minimums given here. Specifying the tying requirements. Don't just leave that to the iron workers in the field. If possible, go for welded joints. Use that equation to estimate and calculate your stiffness, and really, recommend and urge to get that field measurement, to get the deflection, to verify your stiffness calcs. Make it a separate operation if possible, so you have time to react, and then modify your stiffness properties if warranted. Furthermore, when it comes to the crane plan and rigging, like any good crane plan, got to visit the site. Not doing it from behind your desk successfully, guaranteed. You got to collaborate with all the parties on the crane selection and rigging methods and preferred practices. Be careful on the weight determination. These get pretty hairy a lot of times with all the miscellaneous bars. You can't speed through that. And of course, the center of gravity is going to vary. Then a decision has to be made. You want to use pickup bars or a lift collar? Again, site specific, depends on many factors. You should just know that you have both options. Reasonable number of rigging points needs to be determined. Again, it's site specific. Yes, it's generally 20 to 40 foot uncentered. A lot of variables go into that. Diameter of the cage, amount of rebar, the tying, the experience of the ironworker. Anyway, once you've got that far, you want to analyze your horizontal, 45-degree, and vertical configuration. As we showed earlier, crane loads shift from one to the other, rigging also loads, and consider all your temporary support requirements that are a result of the splicing choice. Use U-bolts or wire rope U-bolts whenever possible. They're very reliable. Make sure you get them tested, and put a factor of safety at 2. And just to repeat what we spoke about earlier kind of quickly, the cage less than 20 foot, you really have no issues, right? Easy. Between 20 to 40 foot, a single crane with 1 block should still be adequate. You probably go to 2-point rigging, though. At that point, what gets difficult is the 40 to 140 range, where you're going to be using a crane with 2 blocks or 2 cranes. One of those cranes might have 2 blocks also, ideally. And you definitely have multiple point rigging, spaced according to the requirements of the particular shaft or slurry wall cage. And then above 140 foot, you're really probably looking at a lift table. So finally, for fabricator, not that he's the last guy, but he's the last guy in the chain, you might say, of putting these things together. For prefabrication, the template hoops should be at least number 8, 10 foot, 100% tied with strong ties. Your internal bracing should be at least 4 number 8s tied, and you need your 4 pickup bars, of course, with double saddles. So when we talk about all these 100% ties, the rest of the intersections do not need to be tied. You're not really gaining much. You're spending a lot of money and time. Tie wire should be the stronger 15 or 14 preferred from domestic sources. And yeah, you got the experience, you got the less experienced guys. Place your people properly for the critical joints. Consider using alternate bracing, such as the cage right system that Ben spoke about, or structural shapes or similar. There's not one size fits all. And consider using a lift collar instead of the pickup bars. And when it gets to the rigging and lifting, be prepared to do that deflection survey. We know there's always going to be some trial and error involved and adjustments necessary anyway. So best to do it as a separate operation, and this way you avoid dragging on the ground and compromising the quality of the cage for the final product. So with that much said, we recommend 3 things for all parties. That the risk management be properly implemented and shared, consistent with protocol for other lifts. We don't want to just rely on the ironworker foreman for complete responsibility. And recognizing the importance of worker safety above all else, we really should be sharing information for the good of the industry, taking our cards away from our chest somehow without fear of litigation. And to the extent possible, if there was any way we could convince the authorities to free up some funding so Dr. Atani or others could do additional research, this would be great to improve the guidelines, develop them, broaden the scope, and make this a safer world for all of us. Because we really don't want to be this guy, do we? Of course not. We want to be this guy, protecting everybody from those mess of swords and number 11 rebars flying into the air, being aware of the hazards, ready to protect. We want to read up and purchase these reference documents and make for picture-perfect rebar cages. Well engineered and executed non-event. So with that, that concludes our presentation. Sorry for running a couple minutes over. Hope you're all still there.
Oh, that's great, Vince. Thank you so much. We're pretty good time-wise. I got a few questions that came in. If you guys are okay with it, maybe I can get you 1 or 2. And again, we want to respect everybody's time and not go too far over, but I think we're okay time-wise. Is that okay with you, Vince and Ben?
Yeah, definitely.
Okay. Why don't we start with this one? Brian asked if you guys could speak to cost differences between field assembled cages versus shop assembled and then shipped cages. And just in your experience, if you could speak a little bit more on that.
Well, we're probably not the best to speak on that because we're mostly working in a New York City metro area where it's mostly field fabricated. And, because of the difficulty in transporting these cages into the city, that's typically not an option. I got to believe, the people that can do have them prefabricated. I would refer you, I guess, to Dimension Fabricators. That's our local source. And I'm sure they're going to tell you they're a lot less.
Okay, yeah, thank you.
Fabricators is in Scotia, New York, as a start.
Alrighty. Let's just tackle one more quick one here, and then we can let everybody get on with their day. So can you then speak about limiting deflections so as not to damage pile cage instrumentation, so CSL tubes, LV, TDs, O cells, etc.?
Well, that's a good question, and most of that stuff is pretty flexible with the exception of the O cell, which is typically right at the bottom. We typically like to put a rigging point right near the O cell so that doesn't flap around. And, all shops have this instrumentation, and like I said earlier, if you're rigging in the 20 to 40 foot range, that typically doesn't create any kind of damage, and we're seeing deflections of, not a foot, but not, an inch. We're probably somewhere around 6 inches deflection. And that seems to not be a problem. That's a very good question also. I hadn't really thought about quantifying that. But, that's, my gut feeling is around 6 inches. Seems to work well.
Okay, great. Well, there are a couple more questions, and then I got one or two still flowing in. But again, we slotted this thing for about an hour, so this feels like a good time to wrap everything up. I'm going to grab the screen back very quickly here. Just so everybody's aware, we're able to get professional development hours for attending this webinar. So please go to iti.com/pdh, and also we will post a recording within 24 hours. And if there's any follow-up questions or there's something that you guys think about later, please email them to me, and I can get them to Vince and Ben. My email address is jonah, Jonah, @iti.com. So that's it for Showcase webinar today. Vince, thank you so much. If you have anything to say to our audience, we still have folks on the line.
Well, no, I appreciate everybody attending. It looks like only a few people dropped out, which is nice to know, because we have a little head count that shows up on our screen. And basically, based on those questions, I'm gonna do a little bit of research, because there are two really good questions you had there, and I'd like to formally respond back to you all. Jonah, maybe you could post the answers.
Yeah, absolutely. Thanks again to you, Vince and Ben, for your guys' time, and feedback so far I'm getting is all positive. So thank you, everybody, for taking time out of your day and joining us. Look for the next episode of the Showcase webinar series in late February. We are going to talk about how to build your crane and rigging library. So that should be definitely a different point of view than this month, but should be good nonetheless. And I'll open registration up on that one here shortly. So thanks again. Everybody enjoy your day, and thank you.
Take care.
Thank you.